Hi there. As you can see, today we're talking about electron configuration. Now, I know what you might be thinking.
What?
Okay, but you might be thinking that how can we come up with the arrangement of the electrons if Heisenberg uncertainty principle says that we don't know where the electrons are? There's two parts to the answer. Number one is that we're still talking about probabilities. The second part, and the more important part, is what we're going to be talking about in when we say arrangement, is what sort of energy the electrons have. So we can still come up with an idea of how much energy the electrons probably have, and we still do that with a fair amount of confidence. However, our starting point takes us back to the quantum numbers. So if we think back to those quantum numbers, if we have a value of n, our principal quantum number, we then have possible values for L, our secondary quantum number. And you'll notice I left a bit of a gap there, and I'm going to fill that gap in the next line. Now, we know that these L values can be assigned letter values instead of numbers, and we haven't really needed that a whole lot yet, but we will start to use that when we start identifying electron configuration. The next important thing is the M sub L values, our orbital numbers, where each possible value represents a possible orientation for the orbital. So we have our M sub L equals 0, there's only one orientation, and then our next one, our p orbitals have 3 possible orientations, and our d orbitals, L equals 2, 5 possible orientations. And we also learned a little while ago that we can represent each one of those groups of orbitals, or in the case of one of them, just that orbital, but we can represent those using boxes. So again, we're not coming up with anything very physical in our model, but we're representing the mathematical possibilities this way. And then of course we know how to fill in those boxes with arrows representing electrons either spinning +1/2 or -1/2. Now, depending on the timing of A, when you're watching this, and B, whether we did this the previous day or not, you may or may not remember the sheet. But what we did with this sheet, if we did it, or what we'll do with this sheet when we do it, is we'll start filling in the sheet for the electrons in atoms. So if you look at this sheet, you'll notice that it starts at hydrogen and works its way down to, I think it's argon. But what we do is we start adding electrons to atoms using those boxes. So each column, and you'll notice that there's one column of one box, there's a column of a total of 4 boxes, 1 and then 3, and then the next one is 1, 3, and 5. So as we're building our atoms' energy levels, we're building A, the number of boxes possible, B, the number of different types of boxes possible. And then we'll fill in the electrons. And if we have gotten to that, then we will dealt with atoms that have more than one energy level. How do you do that? When do you move on to the next energy level? When do you move on to the next sub-energy level? If we were to take a look at the electrons and oxygen, and either you can think back to what you did or you're ready for what we'll do, is oxygen will look like this. So oxygen has a total of 8 electrons, 2 in the first energy level, 6 in the second energy level, where it also then has those 6 in the outer energy level that are the valence electrons. So it ends up looking like this. Now again, if we haven't gotten there yet, we will. If we have, then this is what we did. We could identify each one of those orbitals with a number for the energy level and a letter for the sub-energy level. So it would look like this. Oxygen has electrons in the 1s, that's your first, and then in the second energy level, it's broken down into the s sub-energy level and the p sub-energy level. So we could then say that oxygen has 1s2, so the little 2 means 2 electrons in the superscript rather. So 1s2, so 1 first energy level, s type orbital, 2 electrons, 2s2 and 2p4, because if I count up all those electrons in the p orbital, there's 4 in total. And I don't really differentiate between the different types of orientations, or sort of not different types, but the different orientations. Each box translates into one of those values. Now, if I look at the whole periodic table, because what I don't want to have to do all the time is build the atom from the bottom up. I look at the periodic table and notice there's fairly distinct sections. There's 2 tall columns on the left, the 6 taller columns on the right, the section in the middle, the transition metals, and then the very, very bottom, the inner transition metals, the last 2 columns. Now, different periodic tables might have different numbers, different blanks or whatnot in row 7, but we don't really care. We may or may not have taken a periodic table and done this to it. and colored it. And the idea is that you'll have this before you watch the video, but timing being timing, you may or may not. But this is what we'll do, or what we did to the periodic table. I take each one of those sections and we're going to make it a separate section. And we're also going to label it. Now, if we have not done so already, you don't have to worry about doing this on your own. We'll do it together in class. What we'll do is now learn how we're going to use it for coming up with electron configurations. Now, one of the things, of course, is we moved helium. We've identified each section using a letter value that's going to correspond to a value of L, and how to identify the N value. So those numbers, those things in the circles might not make a lot of sense to you right now unless we've already seen it. If we've already seen it in class and they still don't make any sense to you, we're going to have to solve that problem first chance we get. And then finally, of course, we have the fourth section. We will also identify the rows. And that's where we get that N is row number -1 or row number -2, or N is row number, is based on the actual row number. So how are we going to use it? We're going to pick an atom. So in this case, I'm looking at germanium. So I find germanium on the periodic table, and now what I want to do is I want to start from the first atom and work my way across the periodic table through the rows until I get there. So I start with atom number 1, or electron number 1, position number 1, and I go all the way across that row, and I finish up with 1s2. Work my way across the second row. Now my second row starts at 2s2, and then I jump across that gap and I do the rest of row number 2, and that takes me all the way through to P6. And then I start row number 3 and I do the same thing, and then I start go all the way across row number 3, so my 3s and then the 3p, and then I start row number 4. Now row number 4 starts out the same way it has all along, 4s2, but once I jump into, or not really jump, but once I go from the 4s into that next block, it's row number -1. So the next block is not 4, it's a 3, and is row number -1. Fourth row, but 3d. So that's a 3d, and if you count them all the way across, you have 3d10. Almost there. Now I'm back into the tall columns, and that's N is row number. So my next one, the last two, actually are 4, because N is row number, P, because I'm in the P block, 2, the last 2 electrons. And if you would count up all those electrons, you would find that they would have the correct number for germanium, which is 32 electrons. I would write the electron configurations as you see, as you see on the bottom, 1s2, 2s2, 2p6, and so on, all the way up to 4p2. Now, you might be thinking, there's got to be a shorter way, because we only did 32 electrons there, and the periodic table has a lot more than that. Good news, there is a shorter way. And the shorter way involves putting the last element in the row, which is the previous noble gas, in square brackets, and that represents the core of that atom. And then write the remaining row. Well, what if it's a noble gas? Same thing, you would just have a longer row to do. So for this one, the previous noble gas is argon. That takes care of the first 18 electrons, and now you have to do, go back to that, now you have the remaining few to get up there to the 32. Okay, let's try that for bismuth. So we're going to do the electron configuration for bismuth based on the short form. So I find the previous, I first find bismuth, then I find the previous noble gas, xenon. That takes care of a bunch of electrons. Now I only have to do the last row, which is row number 6. Row number 6 will involve -1 and so on. So, cut across row number 6, 6s2. I start row number 5, I go across there, but you'll notice the numbers, I go from, was it 57 to 71 or something like that. So I actually have to remember to jump down to the row, the very, very bottom of the periodic table to get across the F block. And when I do that, that's 4, because it's row number -2, 4F14. And then I go back to my row, the D block, and then I finish off the last 3 electrons in the P block. So my electron configuration as it stands is that 6s2, 5d1, 4f14, 5d9, 6p3. Now, I could leave it like that, because that's correct and that's the order that they're going to fill, but I can also combine those d electrons into a 5d10. My word of caution to you right now is don't try to do that all at once. And what happens is people often scoot all the way across row number 6, forgetting about those F electrons. So we'll have to make sure that on your periodic table we sort of have some little visual trigger to send you down to the bottom of that of the table to get the F electrons. Now, again, if we have, great. If we haven't, we'll get it. But we've done something, we've highlighted the chromium family and the copper family and said they're going to do something a little bit special. We're not going to deal with that in this video. We'll deal with that in class. It'll make some sense, I think, but what we're going to do is we're going to look at orbital box diagrams for a few things. We're going to figure out what's going on with those, and then we're going to see some patterns that develop, and then we're going to say what happens differently in the chromium family and the copper family. Okay, this might be you right now. Hopefully not. But the last thing I want to say is, again, like a lot of the things, if we follow the pattern and be fairly systematic, it actually works out fairly well. From here, we can actually start to explain some things. Like we can explain why iron, for example, has the possible charges that it has. We can explain why certain things behave the way they do. We can explain why chromium is a very, very stable metal and why gold is a very, very stable metal and not reactive at all. So in the same way that understanding the structure of the atom tells us about its properties, this electron configuration stuff, not this, the head exploding, but the electron configuration stuff tells us a lot about structure of the atom. So then we can understand its properties. We'll talk to you in class.